And so now we come to the equations. This is probably the first really significant section of any physics book, and that's where you get the basic equations for deriving distance, velocity, and acceleration. What basically, for example, if you want to find what the velocity, and these all assume constant acceleration. So let's say that you know what the starting velocity was, and you know what the constant acceleration is, and you know how long. So you have v1, the initial velocity, you have the constant acceleration, which means it's not changing, the acceleration is constant, and you know the time that has gone past, then you can determine what the closing velocity is. Now, I've used v1 and v2 because I think that's just more intuitive. A lot of Young and Freedman use v0 for the initial or origin, the origin velocity, and then just a v for the velocity at any other point. But I think it's more intuitive to think of it in terms of v1 and v2. Also, because in this chapter they're only thinking about motion in one dimension, so we're not thinking about a winding road or up and down. We're talking about straight line motion, so you have like a vx or v0x. I just think that gunks up your mind. And so this is assuming straight line motion, but the second velocity is equal to the first velocity plus the acceleration and the amount of time. And so you can solve and determine what the second velocity is. You don't need to know the distance in order to figure out using this equation. Each of these equations that on this page leaves something out. And so if you have some of the variables but not all of them, you just pick whichever equation has the variables that you actually have the information about. So this is the equation you would use if you don't know the distance that was covered, but you do know the starting velocity, the acceleration, and the amount of time. So that's very standard. V2 equals V1 plus AT. That is probably the first physics motion equation that you should learn. The second is the distance equation. So let's say that you don't know the end velocity, but you know the velocity it had when it started, you know the amount of time, you know the constant acceleration, and you know how far along it was when you started. Now, of course, if it started at 0, take the first equation. If it started at 0 velocity, that v1 just disappears. Or if it started at a distance that you're calling distance 0, then that x1, just disappears, and it simplifies the equation. But basically, if you want to know the place on the road, if the road is completely straight, and you want to know the place on the road that you're going to end up, if you know the place on the road that you started, you know the velocity that you started with, you know the acceleration throughout that period, and you know the time, then you can solve for what distance, how far you're going to get in that amount of time, starting with that velocity and at that acceleration. So this is, again, by the way, AT, the acceleration is in meters per second, say. That's the kind of thing, or meters per second square. Time is in seconds. So meters per second squared times seconds, well, one of the seconds on the bottom is going to cancel out, and that second on the top is going to cancel out, and so you're left with meters per second. So AT, when you multiply those, the labels that go with it, meters per second and seconds, by each other, you're going to end up with meters per second, which is a velocity or a speed. What I'm trying to get at is if you look at the way that these things that are being multiplied by each other, if you look at the way their labels go, they end up with distance, for example, in the second one. So velocity, let's say meters per second, times second, the seconds are going to cancel out, and you're left with meters, or 1/2 AT squared. So the t square is going to be seconds squared, maybe, and then meters per second squared is acceleration. The seconds squared cancel out, and you're left with meters. So you end up with an x, which is in meters, a vt, which is in meters, and a at squared that's in meters. So it all makes sense. And if you didn't understand what I just said, the neat thing is that you can just memorize these formulas and use them, whether you understand them or not. You want the derivations? Go read the book. He derives it. You can follow it. It's very easy to see how he can derive these equations using just common sense. They can also be derived using calculus. That's the end of this chapter. Not important again, not essential at least. Here's another formula. So let's say that you don't have the acceleration. You know the distance it ended up, and you know where it was on the distance line when it started. You know the velocity it ended up, and you know the velocity when it started, and you know the amount of time. You don't have to know the acceleration. If it's a constant acceleration, then you know that distance 2 minus distance 1 is equal to velocity 1 and 2 divided by 2 times t. This again makes sense. x2 minus x1 is simply the amount of distance covered. v2 plus v1 divided by 2 is simply the average velocity. Average velocity times time is going to give you the amount of distance covered, which is x2 minus x1. So this formula makes perfect sense if you think through it. The last formula that I find a little bit harder to remember, but the nice thing about the final formula is you don't need to know the amount of time in order to solve it. So the closing velocity squared equals the initial velocity squared plus twice the acceleration times the distance covered. Again, you don't have to be able to derive these formulas to use them. Basically, these are various equations, velocity equations, that you can use in order to find various things about how far or what closing velocity or what the acceleration is, and so forth. So this is the fourth section of Young and Freedman's University Physics, Chapter 2.